This video is one of many discussing the LeCo project, a project focused on studying Legionella control in buildings. The LeCo project is a large, collaborative, and multidisciplinary project. Legionella control in buildings is a multidisciplinary challenge, and to address this challenge, the LeCo project includes 8 distinct but interrelated work packages. This presentation focuses on the topic of work package 1, risk assessment. My name is Tim Julian, and I'm a group leader at AVAG, the Swiss Federal Institute of Aquatic Science and Technology. I will be discussing the LeCo project outputs on the risks of Legionella pneumophila infections from showers. The work I am presenting has many contributors, in particular, Dr. Lisan Tang, whose PhD work forms the basis for today's talk. Showers pose a particular risk and are the focus of our work. Some water supplies in buildings are colonized with Legionella. When a shower is turned on, it generates aerosols from the water supplied, so the generated aerosols may contain Legionella. People taking the shower are then exposed, through inhalation, to the Legionella-containing aerosols. Depending on the person's susceptibility, he or she may then be infected, which can lead to symptomatic illness, including Pontiac fever or Legionnaire's disease. Risks from showers are influenced by the presence and concentration of Legionella pneumophila in the water supply, the aerosol distribution and concentrations generated by the shower, the magnitude and duration of a person's exposure to the aerosols, and the person's susceptibility. For example, people who are immunocompromised or elderly are more likely to become infected. In this study, we applied a method known as quantitative microbial risk assessment, or QMRA, to understand people's risks of illness from showers. QMRA is a conceptual and mathematical framework that models the relationships between exposures to pathogens in the environment and risks of infection and illness. QMRA is an iterative process consisting of 4 interconnected steps, according to this harmonized framework of the WHO. These include problem formulation, in which the scope and purpose of the assessment are defined; the exposure assessment, which estimates the dose of pathogens a person is exposed to along the defined pathway; the health effects assessment, in which the health effects of the hazard are estimated; and risk characterization, which links the exposure assessment and health effects assessment to estimate the expected health effects. It is important to note that QMRA is an iterative process in which the results from the risk characterization can then be used to inform and refine the QMRA through feedback to the other steps. For the purposes of this presentation, we will focus on our application of QMRA to understanding risks of infection from Legionella pneumophila, but there are many resources available to learn more. For example, I recommend the Quantitative Microbial Risk Assessment textbook from Professors Charles Haas, Charles Gerba, and Joan Rose, and the World Health Organization's Quantitative Microbial Risk Assessment Application for Water Safety Management. In this presentation, I'm going to discuss 3 specific work packages that help to inform our understanding of Legionella risks from showers: a systematic literature review of scientific publications in which QMRA was applied to understand aerosol transmission of respiratory pathogens; empirical data collection complemented with modeling to quantify aerosol generation rates; and a QMRA model applied to showers from a water supply in Switzerland with known Legionella pneumophila contamination. We first conducted a systematic review of QMRA studies on respiratory pathogens to identify exposure modeling approaches used to help inform what approach would work best for our model. This work was published in the journal Environmental Health Perspectives, shown here. In this review, we identified 93 research studies, and within those studies, 5 distinct exposure models were used, shown here and further reviewed and described in our publication. From this review, it was clear to us that our model system to understand Legionella pneumophila infections in showers is best describable using a mass balance model, shown in the bottom, in which a mechanistic model of the aerosol generation rates from showers is linked to a person's exposure through their inhalation. An important and understudied factor that influences the risks of infections from showers is the generation of aerosols. We conducted a series of empirical experiments in showers to determine the aerosol generation rates for aerosols of different size classes under various different conditions. Aerosol size matters because the size of the aerosol determines both the likelihood of an aerosol containing Legionella as well as depositing in the lungs. We published this work in Building and Environment, shown here. To do this, we set up an aerodynamic particle sizer in showers, and we measured aerosol generation rates over the duration of a typical shower under different experimental conditions. Specifically, we tested different shower head types under different water temperatures: cold, approximately 26 degrees Celsius, and hot, approximately 40 degrees Celsius. We also tracked concentrations of carbon dioxide over time as a tracer gas to understand room ventilation. In addition to collecting empirical data, we fit the data to models, as shown here for the conventional shower head and cold water showers. We observed increases in aerosol generation rates throughout the shower. Once the shower was turned off, we observed decay of aerosol concentrations consistent with aerosol deposition rates complemented with ventilation. In hot water showers, shown on the right, however, we observed a rapid increase in aerosol concentrations that slowly decayed throughout the duration of the shower before reaching a steady state concentration. Once the shower was turned off, as with the cold showers, the concentrations then returned to baseline, due again to a combination of ventilation and deposition. We do not know the cause of the rapid increase observed for hot water showers, but it has been observed in other studies. We speculate that a thermal plume caused movement of the aerosols to the sampling point, which is supported by our observation of an increase in measured carbon dioxide concentrations. Our final work package included the development of a quantitative microbial risk assessment model to quantify infection and illness risks from Legionella pneumophila in showers. In the exposure assessment, in which we estimate dose, we modeled dose as a function of the sum total of exposures throughout the duration of the shower, based on the concentration of Legionella pneumophila in the source water. For this concentration, we used data collected from a public shower facility in Switzerland with a known history of contamination. In addition, we considered the concentration of aerosols of each size class generated throughout the shower, the proportion of bacteria that partition into the aerosols for each size class, the deposition efficiency of each aerosol of size class at the alveoli, and the breathing rate. This work is based on a manuscript that's currently in preparation. A notable aspect of our study is that we also accounted for dynamic Legionella concentrations in water supplies. Shown here is a figure from Grimard-Cagnier published in Frontiers Water in 2022 that highlights that concentrations of cultural Legionella pneumophila, shown on the y-axis, are frequently higher in the first flush concentrations, the gray box plots, than in the subsequent composite samples, white box plots. In our study to estimate infection risks, we used data collected from a building with known contamination of Legionella pneumophila in Switzerland. On the right is a histogram of cultural Legionella pneumophila concentrations from the composite samples of the cold water line in this building. Concentrations were high, regularly exceeding 1,000 most probable number per liter in approximately half of all samples. For each sample collected, we had paired first flush concentrations, and so we could model dynamic concentrations of Legionella pneumophila over time. Once the dose is estimated based on the exposure assessment, a probability of infection for a given exposure is estimable based on published dose response curves. For Legionella pneumophila, we relied on an exponential exposure model as identified through our previous systematic review. We then extended the risk estimation to an annual probability of infection by accounting for the total number of exposures in a year. For showering scenarios, we estimate that people take on average 1 shower per day. Our resulting QMRA model allows us to estimate for every combination of Legionella pneumophila concentrations in a first flush and composite sample the risk of infection. Shown here is the infection risk for a cold water scenario, in which we assume aerosol generation rates we measured for the cold water scenario, as well as the composite Legionella pneumophila concentrations measured in the cold water line. The red line represents the concentrations at which the risk of infection is 10 to the minus 4 infections per person per year, a commonly used benchmark in QMRA, which represents that 1 person out of every 10,000 is infected per year. The points represent the samples collected from the building in Switzerland, showing many of the showers are contaminated at unacceptably high levels. On the right is the same graphic for hot water shower scenarios. Here, the risk benchmark is lower, due primarily to the higher estimated exposure to aerosols for hot water conditions we observed in our previous study. As a consequence, a substantially higher proportion of samples are contaminated at unacceptably high levels. Here, it is also important to note the concentrations for Legionella and pneumophila in showers in this graphic are much higher than we would expect to see at an average private household or facility in Switzerland. Indeed, as you'll see in other outputs from the LeCo project, many of the households we tested in Switzerland did not have detectable Legionella and pneumophila. Our QMRA model also provides an opportunity to investigate the factors that influence infection risks. Shown here is a graphic that plots the impact of multiple different model parameters on the annual risk of infection. By decreasing or increasing the value of one of the parameters, we can influence our risks of infection. For example, we observe that reducing the pathogen concentration in water, shown in purple, by 80% from the baseline, we reduce our risk of infection below the 10 to the minus 4 benchmark. Similarly, increasing the shower stall volume, which dilutes the aerosol concentrations, can also reduce our risks. From our model, we generally see that controlling Legionella and pneumophila concentrations in water supplies, both the initial concentration and steady-state concentration, is important. Similarly, reducing aerosol generation rates can help to reduce risks. In this graphic, we observe that ventilation, which also reduces aerosol exposures, has limited impact. This reflects that ventilation in the baseline scenario is likely already sufficient. If areas with little to no ventilation, substantial increases to remove aerosols can be important considerations. In our QMRA model, we highlighted specifically a scenario in which Legionella and pneumophila concentrations in buildings are high. As you will see in other presentations from the LeCo project, most private buildings do not have Legionella and pneumophila contamination, and amongst those that do, many have low concentrations. Together, this information highlights that showers can pose a real and meaningful risk of legionellosis, but that other exposure scenarios beyond showers may also be important. In this context, it is important to raise awareness of risks of legionellosis amongst the most vulnerable, including raising awareness for private testing of showers. For showers contaminated with Legionella and pneumophila, we should also be promoting simple risk mitigation strategies. Examples include reducing flow rate, reducing shower durations, showering at cooler temperatures, and increasing ventilation. However, it is important to note that the relative impact of these simple strategies depends on site-specific conditions. No universal recommendation for simple risk mitigation strategies is sufficient to reduce risks to safe levels, highlighting continued need for support testing and water safety management plans. I would like to acknowledge the large group of people involved in the work presented here. Specific acknowledgement is given again to Dr. Li-Tsung Tang, who completed his work in the context of his PhD dissertation. I hope you found this presentation interesting. For more information, please see the resources highlighted in this talk. If you have specific questions or comments, feel free to contact me directly at the email address here, or visit the main page and post your question using the questions and answers link. Also, if you'd like to learn more about the LeCo project, please be sure to check out the other videos.